Hello and welcome to Acoustics Part 1. My name is Scott McDonald. I'm an application engineer here at Siemens, and I'm going to be your host as we go through a couple hours of acoustics and some of the things we need to keep in mind when we are working with sound. So as far as an agenda goes, we're going to talk about some of the fundamentals that go into making a sound pressure measurement, and realistically, sound pressure measurement is almost the only measurement we can actually make for acoustics. There are other values that we're going to talk about today that we can calculate and build off of our pressure measurement, but really it comes down to these fundamentals. We're going to talk about some real basic stuff we have to understand. And one of those is the sound field. Where we're taking this measurement can have a big effect on what we measure, and so we're going to talk about those a little bit. We'll talk about one of these quantities that we can calculate, and that's called sound power, and what this quantity is and why it's useful. And then we'll talk about two of the ways we sort of work to control sound, and these quantities, absorption and transmission loss. And we'll talk about how we test for those, what the values mean, and what we can do with them. Okay? So sound pressure fundamentals. This is really the building blocks of everything. And one of the things that's going to be really important to keep in mind as we go on today is this idea that the human ear and the auditory system that we have with us, our brain and our ears and everything, is not equivalent to these microphones that we are almost always using for our measurement. They're just not the same thing. And so we use some analytical tools, a lot of which we'll talk about today, to take these microphone measurements and make them more useful or applicable for working with sound for a human being. Okay. And one of these ways is that the microphone responds to instantaneous pressure, right? These pressure waves are coming through the air and hitting our eardrum, and it's an up and down pressure oscillation, but that's not how our brain registers the sound, right? It sort of takes these groups of those oscillations and reports a single number to our brain. That's how loud it is, right? This is how we get something like the RMS, or root mean squared, of a sound pressure level. That's how our brain hears, and we have to do some math on this microphone signal in order to make it mean something for us. Okay, so one example, but this theme is going to kind of come up over and over today. So if I took the human hearing domain and I put it in a blue shape here, this is what we would get. And you see this is the frequency axis down here, and this is what we'll call level or amplitude, volume, if you will. And essentially this shape means that we can hear everything inside the blue area, and outside the blue area we cannot hear. Okay, so if we hear it, it's in this blue hearing domain. And we see music and speech are obviously subsets of these, but if you just look at this overall big blue area, what does that shape kind of remind you of? We ask this question a lot, and the most popular answer I would say is the map of the United States. It kind of looks like the contiguous United States, right? And this is a very useful model for us because it helps us to sort of describe some of the features we see in this shape and sort of recall a state of the union that maybe helps us remember some of these effects, okay? So the first we like to talk about is this shape out here on the left side of this graph. This would be the state of California, let's say. It's distorted, but work with me here. So the California effect is what we would say this effect of our hearing is, and this is really that we don't hear very low at well frequency, right? If I'm an ant walking along the western coast of the United States, and I keep falling in frequency, going from 200 to 100 on my way down to 50 hertz down there, I have to keep increasing the amplitude, or walking north as well as west in order to stay on land, right? So as the frequency drops, we have to keep increasing the level to keep it audible. We don't hear very well at low frequency. Okay, that's the California effect. Out here on the eastern seaboard, it's sort of a vertical line, right? What does that shape suggest to us? Well, it says that beyond some frequency, it doesn't matter how loud you make it, we're not able to hear it. Okay, so this is the upper threshold of our hearing. We'll call that the eastern seaboard effect. And the other effect we like to talk about is this little dip down here. So the southernmost part of the United States, that's Texas, right? So the Texas effect is talking about this dip. And what does this dip tell us about our hearing ability? Well, it says, here between 2 and 5 kilohertz, let's say, we can hear a smaller pressure, a smaller amplitude more so than anywhere else in the hearing domain, right? So we hear better in Texas frequencies, 2 to 5K, than anywhere else, okay? So the Texas region and really the frequencies associated with it are going to be really, really critical to understand and keep in mind when we're working with sound for human beings, because we're going to remember how well we hear there. And so sounds in this frequency range are going to be more and more prominent to us when we listen to them, okay? So Texas effect, California effect, Eastern Seaboard effect. Now, if we take the sort of the hearing range of the human being, we use descriptive words from like barely audible all the way up to something that's so loud it's painful, and we look at the root measurements and the values we would get for those descriptive words. Again, we're using a microphone. Those measure pressure, so we get Pascal values, right? Down here at something barely audible, that's going to register on our microphone at about 0.000063 pascals. Okay, that's a soft whisper. Moving up one descriptive word, our bedroom at night, pretty quiet, 0.00063 pascals. And so on up the chain to something very loud, 0.63, heavy truck, and then something so loud it's painful to listen to, like a jet taking off, that's 20 pascals. Now, what do you notice about this range of Pascal values? Well, first of all, you sort of notice that every time I go up a descriptive word here, I'm just dropping a zero, right? 0.00063, 3, 2, 1, no zeros, right? And so there's some sort of power of 10 thing going on here. But I also notice that it's not very often that I'm working with numbers like 20 at the same time I'm working with numbers like 0.000063. The difference between these two numbers is huge. And so it tells us the human hearing dynamic range is this really wide range of values. We can hear from very, very small pressures all the way up to pretty big pressures, okay? And so this dynamic range means that working with the Pascal value for noise measurements or sound measurements isn't very convenient, right? We have this huge dynamic range, and I don't want to be responsible for writing down 4 zeros before I get to my first significant digit, right? So it has to be a better way, and that's where this guy comes in. This is the decibel. And the decibel is one of these tools that we use to help us work with sound, okay? And so you see if I convert those Pascal values into decibels, I get some much easier to handle numbers, right? It's not only is this dynamic range sort of squashed, 120 is a lot closer to 10 than we saw in the Pascal equivalents, but also this sort of nice round numbers, right? 10, 30, 50, 70, 90, 120. Those are all nice round, easy to work with numbers. Okay, so the decibel is our first analytical tool we're going to use. So how did I do that conversion? Well, the decibel is really nothing more than a logarithmic ratio between two values, okay? So I have some pressure that I'm measuring with my microphone. I divide that pressure, that Pascal value, by some reference pressure. In this case, the sort of accepted pressure reference is 20 micropascals. So let's say I measure 10 pascals, I divide that by 20 times 10 to the negative 6 pascals, take the logarithm of that ratio, and then multiply it by 20, and I would get a dB value, okay? Decibel is used a lot in acoustics, but it really inherently has nothing to do with acoustics. It was developed in the telecommunications industry and for transmitting telegraph signals over long wires. And so it's really just a logarithmic ratio of two values, but it's very convenient for working with sound, as we saw in that last slide where our descriptive words have nice round decibel values, okay? So I call this sort of the original sound quality metric. It's the first tool we use, and we've been using it for a long time, to make working with sound more easy, for lack of a better phrase there. But our hearing perception to amplitude is sort of logarithmic in nature, so we use a logarithmic unit. Makes perfect sense. So it makes it very convenient. However, there are going to be some oddities because it's logarithmic that we have to kind of get used to, and let's see what I mean. So let's take a couple sample pressures here in this middle column and their dB or decibel equivalent over here. Let's start with this nice round value. 1 Pascal, I convert that to decibels and I get 94 dB. Okay, good enough. Now let's double this Pascal value and I go from 1 Pascal to 2 Pascals, right? And I've increased by 1 Pascal here. My decibel value increases by 6 dB, right? 94 to 100 decibels, 6 dB increase. Fine. Now I'm going to double again. I'm going to go from 2 Pascals to 4 Pascals. You notice this increase is twice as much here as it was here. But what about my dB increase? 100 to 106. 6 dB again. Okay? So even though this jump is twice as big as this jump was, I had the same increase in decibel values. So a 6 dB increase in decibel values indicates to me a doubling of the sound pressure level. It has nothing to do whether it went from 2 to 4 or 20 to 40. I would always register a 6 dB increase there, okay? So this can take some getting used to, but it's just something we're going to have to do in order to work with the decibel, okay? So 6 dB is a doubling of the sound pressure in pascals. However, there's another thing we have to worry about with decibels, and it's that they don't tell us a complete story. For instance, can you hear, or let's say our machine makes 30 dB. Hey, Steve, is 30 dB a problem? Well, I don't know, right? 30 dB, is this a problem? Well, is it 60 hertz? We can't even hear 60 hertz at 30 dB. However, if that machine is making 30 dB at 200 hertz, we can hear that, and it might be a problem, right? So just the value in decibels isn't enough information. We also have to sort of report some frequency information to recall this hearing domain and understand whether it's going to matter to us or not, okay? And we're using a microphone to measure all of these noises, right? And the thing about it is the microphone, assuming we're using a nice high quality engineering microphone, they're made specifically to measure all frequencies equally well, right? You'd get a cal sheet and this nice flat line says, I don't prefer, as the microphone, I don't prefer one frequency over the other, and the amount of signal I output at any given frequency is going to be the same. Well, we know that that's not how our ear works, right? We saw this with the southern coastline of the United States, our hearing domain. This orange line is the smallest frequency or the smallest pressure we can hear at each frequency, right? It's a function of frequency. And so we're not equally sensitive to all frequencies, but we're using a tool that is. And so we need to use one of these analytical tools to help us adjust a microphone measurement for use with our hearing ability. Remember, we're most sensitive in this case between 3 and 6 kilohertz. We don't hear very well at low frequency, and so we have a new tool, something we'll call A-weighting, which is a simple correction for a microphone measurement to try to induce some of these human hearing effects, okay? And we have a new label. We would not just calculate dB, but dBA, indicating to our recipient that we've A-weighted these decibel values. So how does this dBA thing work? Well, this is the A-weighting filter, and you see it's really just an attenuation versus frequency, and it's sort of a simple curve because it's been in use a long time, right? When these started, they were literally soldering resistors, capacitors, and inductors together to make a mechanical circuit to use and apply this filter, and so it had to be sort of simple in shape. You see it attenuates low frequencies, and it even includes the Texas effect here, right? It goes above and it's amplifying between 1 and 5 kilohertz here, okay? So it's capturing some of these effects. So how does it work? Well, let's say we measure 70 dB and we at 100 hertz. So we measured a sine wave at 100 hertz and we registered with our microphone 70 dB. So I'd come over here to 100 hertz, go up, and it says subtract 20 dB at 100 hertz. So we would report 50 dBA. If we measured 70, we would report 50 for dBA, okay? So it's just sort of a simple attenuation we do frequency by frequency based on this curve, okay? And you might not immediately see the similarities here, but this is an attenuation filter. But if I flip this shape over, you can kind of see the California effect, Texas effect here. It's a nice simple shape, but it captures quite a bit of our hearing ability, okay? So this is sort of an extension of our dB value sound quality metric, we're now going to A-weight it to bring in some of the frequency sensitivity of the human ear. Okay, so that's what A-weighting does for us. Now I'm going to do a quick little demo here. I've got Test Lab running. I've got a Scatus XS here hooked up with a little single microphone, and you can see as I'm talking, I'll see if I can set that down and it'll still pick it up here. But as I talk, you see the frequency content updates live here. And so I'll just sort of whistle. And I'll stop it there. And you see my whistle, human whistle, is actually quite close to a single frequency generator, a sine wave generator. So you see basically all my amplitudes at one frequency. And I can come over here and I'm going to increase this format so we can read it a little bit better. And so we see pascals over here, and my limits, I'll increase those as well. And so you see I've got about 0.35 pascals for my whistle there, right? So we first talked about decibels, so I'll right click on here and I'll change the format from amplitude to decibels. And you see that Pascal value was about almost 85 dB here. But what is all this content out here? You notice I didn't see any of these before. If I put this back in amplitude, looks like I really only have one frequency going on. Where did all that content come from? Is that content not really there? No, it's there. The decibel value, part of the reason we use it is because it squashes this dynamic range. And so all of our small values kind of get brought up compared to our highest value, okay? And so these are just really small pressure values converted into decibels. So this is dB, it's about 85 dB. And depending on how good you are at frequency, see if you can guess what frequency that was. Bring this guy over, and it was about 1978 hertz. Okay, so almost 2 kilohertz. I'll move that right to my maximum, 1975. 8491 decibels, okay? So that's where we see our decibel value. Now we can also A-weight this, and I just come in here and under processing, I can put on A-weighting here. Now, do you think the amplitude is going to go up or down when I A-weight it? Now remember, we're going to attenuate all these frequencies here, California effect, but we're also going to amplify in the California region. So is my whistle in the California region? Well, let's find out. 84.91, linear weighted, 86.1. So yeah, my whistle is dead set in the middle of Dallas, Texas, or maybe Austin, the capital, and it's right in the middle, and so I'm actually getting amplified by the A-weighting filter, and we see that by the amplitude going up here, okay? And so that's a quick demonstration of how decibels and A-weighting work, and yeah, so let's jump back into the presentation here. So that's sort of a frequency spectrum we see in green here. You may have seen these blue lines here before. What are these things? You may have seen this on a plot like this. Well, these are something called the octaves, octave band. And this term octave is borrowed from music theory. And the oct part, it means that there are 8 whole tones between notes of the same name. On a piano keyboard, you'd start out with, this is the A key, and this is the A4 key. If I go up 8 whole keys, I end up at an A again. And you see the frequency doubles between A4 and A5. So 440 hertz, 880 hertz, and we would say this is 1 octave. We can go up another couple octaves, and you see this frequency doubles every time we go up an octave. Okay, so this frequency doubling is part of what I want to have register in your brain when you hear the term octaves, double frequency, okay? And octaves, when we plot our frequency spectrum in terms of octaves, all it really means is that we are taking a group of frequencies in our narrow band. All of these amplitudes are getting summed up and reported at a single value for that frequency band. Okay, so we sum up all the noise energy over that band and we report it at a single number. Okay, so we're grouping all these amplitudes. But you notice this guy is twice as wide as this guy, which is twice as wide as this guy, and so on, because each octave band contains twice as much frequency information as its lower frequency neighbor. Okay, and typically we'll plot this on a logarithmic axis so that they all look like they're the same width, but you notice that the value is doubling every time we have a hash mark on this equally spaced x-axis. This is a logarithmic frequency axis, so it makes our doubling columns look the same width. Okay, and these are the center frequencies for the human hearing ability broken into whole octaves. And there's also something called the 1/3 octave, which is just the full octave band broken up into 3 subsets. And these are the center frequencies for the 1/3 octave band. And some of these numbers might look familiar to you depending on how fancy your stereo equipment was. You may have had a graphic equalizer that had these frequency values on it, and they are basically little volume knobs that you have for each of these 1/3 octave bands. Okay, and you could turn the volume of the singer's voice up or down, or the kick drum down here in 100, 200 hertz. You could amplify that sound compared to the rest of them just by raising the amplitudes of that frequency band. Okay? And the 1/3 octave band comes about because these happen to be the groupings in which our brain hears frequencies. We don't really hear in the narrow band, we sort of hear in this 1/3 octave band in terms of groups of frequency. And why is that? Well, if I showed you our auditory chain here from the outer ear, the sound waves come in here to the eardrum, transmit some vibrations to this spiral-shaped organ called the cochlea. And this cochlea has a logarithmic spiral to it, and then attached to the cochlea are all these auditory nerves and that send the signal to our brain. And it's this spiral shape that brings about this logarithmic nature to our hearing. So if we were to spread this cochlea out, or if we take another look at it, we see that each section of the cochlea, as we work our way around the spiral from the outside to the inside, has a different resonant frequency. So high frequencies are on the outside and the sort of entrance to the cochlea. And as we work around the spiral, we get to lower and lower frequencies at the inside. Okay, so each part of this cochlea wants to resonate at a different frequency, and so this is how we sort of figure out what frequency we're hearing. And if I were to take this cochlea and spread it out and label these frequency ranges on it, you see low frequencies here at the right and high frequencies out here at the left. But if you look at, let's say this is however big it is on your screen, it looks like about 2 inches on my screen. So let's say from 2 inches of cochleal space, we only have to cover roughly 1,000 hertz at the low frequency end, right? But at the high frequency end, that same 2 inches of cochleal real estate, I have to cover 13,000 hertz. Okay, so we just have a lot less linear space on the cochlea to register individual high frequencies. So our brain lumps bigger groups of high frequencies together than it does on the low frequency end. Okay, and that's why we can use a logarithmic axis thing like the 1/3 octave bands, where it's grouping these huge chunks of high frequency together, because that sort of models how we hear in our brain. And this is why we hear that way, is because of the cochlea and how much of the frequency range is dictated or dedicated to each square millimeter of our cochlea. Okay, and so the octave band here is really just another way of looking at our narrow band. So I'll activate this picture here. And if we look at that narrow band frequency, I see I have the 1/3 octave band frequency, but you see how spread out the narrow band data is behind it and how sort of smashed together it is out here. The blue and the green are the same information. It's really just whether I'm plotting on a logarithmic axis or a linear axis. So format, I'll go linear. And so now I see these octave bands get wider as I go high in frequency, and my narrow band green looks like it's all equally spaced. Whereas if I put this back in octave, now my octave bands get equally spaced and my narrow band gets spaced out at the low frequency end and squished together at the high frequency end. Okay? So that is the octave band. And if I go back to our software, I can also show, obviously we took this narrow band data, I can show it to you in octave spectrum. And that's what this guy is. So it's these same amplitudes just grouped by octave band, or in this case, 1/3 octave bands. And we report most of our amplitude is right here in about the 2000 hertz 1/3 octave band. Okay, and less amplitude captured everywhere else. Okay, same information, just grouped in groups of frequencies that are a little bit more representative of how we hear. Okay. So that's the octave bands. So again, it's another tool that we have to help us model how we hear. dB was for amplitude, 1/3 octave band is for the frequency axis. We hear in these groups of frequencies rather than discrete frequencies, and so we group them using a mathematical model, which is the 1/3 octave band. Okay? Now there's also something called the critical band rate, or the Bark bands, and this is just sort of an improved version of the 1/3 octave band. It's a little bit more nuanced, it's a little bit more accurate, and so it's used often in sound quality applications. 1/3 octave band is very, very close to these, as you can see if you compare these numbers. This is just a little bit more specific for really specific sound quality applications, but principle is exactly the same. The groups of frequencies our brain hears in. Okay. So sound fields, let's talk about these. Now, if we talk about the free field, we have a sound source here in red, and we have some sound waves emanating away from our sound source. If we are in a free field, that means there's nothing around it, no opportunity for the sound to hit anything and bounce back. It just propagates away forever, never bounces back, and just keeps going. Okay, so if you imagine yourself standing in the middle of a wide open field, that's the free field. There's no trees, no buildings, nothing for the sound to hit and bounce back. In a laboratory environment, obviously this is very hard to recreate, and so instead of just letting the waves propagate forever, we absorb them with these big wedges you see on the floor, walls, and even the ceiling here. This would prevent the sound from bouncing back because the sound leaves the source and then gets absorbed by these wedges. Okay. And sometimes we want to have some reflective surfaces, like this is a hemianechoic chamber, much more applicable for, say, automotive work, where we want to absorb all sound bouncing off the ceiling and walls, but the car is always going to be driving on a road, and so we want that reflective surface. This is most representative. Okay, so this would be a hemianechoic or semi-free field. This is a anechoic environment simulating a free field. The opposite of that is a diffuse field, and this is where the sound is kind of coming from all directions at once. And in a laboratory, we simulate this by creating what we would call a reverb chamber or a diffuse field chamber. And here the walls are highly reflective. They're very massive to kind of reflect all of the energy. And we want the sound to bounce around as many times as possible, sort of illustrated here with this sort of simplified simulation. And you see as the sound waves go out, they bounce off the wall, and they just sort of, all of a sudden, the sound is just kind of coming from everywhere in every direction. And a microphone in here will measure the same pressure regardless of orientation and location in this room. And that's sort of a perfectly diffuse or homogeneous sound field. Okay. So the opposite of a free field is all reflections. That's diffuse field. Now, near versus far. So if we have a sound source here, this guy's kind of right next to the sound source, and we would say he's in what we call the acoustic near field. Okay, so he's close to the source. There's actually what we call circulating and propagating sound energy here. And one of the characteristics of the near field is that there's no predictable relationship between how far away we are and the pressure we'll measure. Okay, it's unpredictable. Whereas the B location is in what we call the acoustic far field. Here we're far enough away from the sound source that the sound source appears almost as a point. You know, we can't tell whether the sound is coming from the top or the bottom or the left or the right. It's just coming from the object. And we are far enough away that these hemispherical or spherical waves coming off our sound source are large enough in diameter that we can reasonably make this plane wave assumption, that we can treat it like a wall, flat wall of sound approaching us, and that approximation is mostly true. Out here in the far field, there is a perfectly fixed and predictable relationship between how far away we are and the pressure we will measure. And this is the law of inverse squares. And this will come up again when we start talking about sound power and sound intensity. Okay, but the far field is defined by this relationship between distance and pressure. Okay, so if we look at this near field and far field a little bit closer, so far field, the sound only propagates. It's kind of simplified. There's, you know, this nice predictable relationship between distance and pressure. In the near field, it's much more complicated. And so we have these circulating waves really close to the vibrating surface of our sound source, where the air molecules are literally trapped and they just move back and forth with the vibrating surface, in this case, like the speaker cone here. Then as we get further and further away, the energy starts to mix, and we have this mix of circulating and propagating. We have a transition zone, and then essentially there's a transition from near field to far field that happens at about one wavelength of sound. Okay, so this transition from near to far is a function of frequency because it has to do with the wavelength or the physical size of the sound wave. Okay, but this circulating and propagating mix is what makes it impossible for us to predict, well, if I move over here, I'm going to predict that I'll measure this pressure. It's too complex a sound field, and so we can't really get away with that in here. Out here, we can make that assessment because it's much simpler sort of dynamically. So sound power. Let's say we're walking across the post-apocalyptic wasteland here, and we come across a set of speakers. And being good acousticians, we ask ourselves, well, how loud are they, right? Well, we're going to make some measurements, right? We're going to use our microphone. We're going to make some measurements. Well, does the distance away from the speaker matter? Will that influence the measurement we make? Yeah, right? For twice as far away, we expect to get a different sound pressure measurement than we would, you know, at 1 meter. How about location? If I'm in front of the speaker versus behind the speaker, is that going to influence my measurement? Sure. In front of the speaker, the sound's designed to come out the front, right? So if we're in front, it's going to sound different than it would behind. And so we have to keep in mind that when we make these sound pressure measurements, they're entirely dependent on the location and direction and sound field that we're in when we make that measurement, okay? How far away are we? Where's the microphone pointing, etc. The idea of sound power is that it alleviates all of those restrictions, and that we're trying to quantify something that is the inherent sound making ability of the object, its power, sound power, that we can measure and report independent of our distance and orientation of our mics and all that stuff. It's sort of an inherent number, okay? And that's why it's valuable. If we make an analogy to a heater, and we were to talk about the temperature that we would make in this room. So we turn the heater on, and an hour later we make some temperature measurements. You know, depending on if we're back here at this lamp, we're going to get a different temperature measurement than we would right up here in front of the heater, right? Those are equivalent to making a sound pressure measurement. You know, if this was a speaker, you made a measurement over here by the lamp, you're going to get a different answer than you would standing right here in front of the speaker. Okay, so temperature and sound pressure are sort of analogous in this case. The heater power, we got it from Home Depot. It says 200 watts, right? That's the electrical power that it's going to use when turned on maximum, let's say. It's going to take 200 watts of electrical power and convert it into heat, right? Well, this is equivalent to the sound power we're after, which incidentally also gets measured and reported in watts, okay? Doesn't matter if we plug this in at your house or my house or at the office, wherever. We plug it in, we turn it on max, and it's going to consume that wattage of electrical heat or energy and turn it into heat, right? That's what sound power is analogous to. It's the inherent sound making ability of our sound source, okay? And so it's indicative of the emitted noise for a given operating condition, regardless of how or where we measure it, okay? And it's useful because of this sort of objective nature of the sound power value. It's an absolute quantity. It only depends on the source itself and the operating condition that so if, we turn it at 50% power versus maximum power, it's going to be a little bit different, but we keep those things constant, we will get the same wattage, right? And ideally, it's independent of the acoustic environment. So we're going to have to keep that in mind, but the sound power value is the sound power value regardless. And that's one of the things that makes it attractive. This is how we calculate it. It's another logarithmic ratio. So we see some powers here, and we'll talk about this a little bit more, but ultimately it's a logarithmic ratio, okay? So why do we use this? Well, it makes it really convenient to compare things across different regions, different markets, different targets, and product specifications, right? We want to say, the government wants to say it has to be so much or it can only be so much or else it's too loud. That makes sound power is a really good way to do legislation because it's an absolute value. It's also very useful for us to compare either us versus our competitors or generation 1 versus generation 3 of our product. As we develop it, it helps us keep track of our improvement and the changes we've made through that development cycle, right? And that's sort of what we're talking about here. Quality control is another aspect where we could test all of our devices at the end of the line, and sound power is going to be a nice objective value that tells us whether we've met some specification or not, okay? So how do we use this? Well, there are a couple different methods. We'll talk first about this pressure-based method, which have a whole series of ISO standards that tell you how to test to this number and how to calculate your number. But we're going to use sound pressure to calculate this sound power value. Another method we'll talk about in the second half of our time together today, and this is intensity-based, which is a whole different kind of approach. We'll talk about that later, but right now this pressure-based method, essentially we're going to take a bunch of sound pressure measurements and we're going to surround our noise-making object. In this case, it's a printer, right? And we've got microphones all around it, on front, behind, left, right, above, and we're going to make a bunch of noise measurements, right? And we're going to use some calculations to come up with this one number over here, okay? This is the sound pressure equation we're going to use sound power equation we're going to use to calculate the sound power value. And it's got a bunch of terms here, and we'll kind of break this down. But this is essentially an average sound pressure over all of our microphones, okay? This summation term here. And then you see this logarithmic ratio over here. This is the measurement surface, or the surface area over which we are measuring. And then you have K1 and K2, and these are correction factors we use for some of the environment things that we can't control. Okay, so K1 is a correction for background noise. Let's say we're measuring our machine on the assembly plant floor. We can't shut down all these other machines around, and so we're going to measure the amount of noise in the background and then sort of subtract that out of our measurement because we don't want it to artificially raise the sound power calculation of our actual machine, right? So we're going to subtract the background noise. Similarly, K2 is a correction for reverberation or reflections of sound might have in our test environment. So if we're testing in this room that I'm in right now, there are walls, and if I clap my hands, the sound travels away, bounces off the wall, and I hear it a second time. Well, that reflected sound is going to, again, artificially raise my calculated sound power number, and so the calculation allows me to subtract the effects of those bounced off reflective sound waves off my number, okay? So let's take a little bit closer look at this equation. I've simplified it and I've removed those correction factors. So just assume we're in a perfect environment with no reflection, no background noise. So let's look at these terms here. This first one is a average sound pressure, right? We're going to sum up all of our microphones from 1 to n, add them all up, and then divide by the number of microphones, right? So just an average sound pressure. And then this is a sound measurement surface area over which we're measuring, okay? And so let's say we're going to measure the sound power of our speakers, and in our lab we have this hemisphere that we're going to use to measure with our microphones, and we set this thing up and we make our measurement and we calculate 100 decibels of sound power. But we have to get this certified by a third-party lab, and so we ship the speakers to them, but they've got a bigger microphone array and a different lab. We better hope they get the same answer, right? We're asking them to certify this product. We said it's 100 dB. Well, they're going to make their own sound power measurements. So let's see how this works. They're measuring at this bigger hemisphere. So what happens to their measurement? Well, the microphones are further away than they were in our test. So their average pressure is going to drop, right? They're further away, so their pressure is going to be smaller. But their surface area increased at the same time, okay? So these two changes are going to sort of offset each other, and they will calculate 100 decibels of sound power. This is how this calculation takes care of the location and distance away our measurements are made, so that we end up getting the same value regardless of how we measured it. Okay, provided we follow the ISO standard and do everything correctly, we will get the same sound power value. And that's kind of how this whole thing is set up. Okay, so that's sound power and why and how we might use it. Now we're going to talk briefly about sound control and some of the things we can measure and use to help control sound. One of these is absorption, the other transmission loss. So when we're making a component, we're going to want to maybe put certain materials in our vehicle, in our airplane cabin or our car, or we might want to wrap our coffee grinder in a certain type of material, right? And we want to know what kind of influence that material is going to have on our sound and how much noise our component makes. Well, when sound energy hits a material, one of three things happens, okay? It could be bounce off and be reflected. It could be sort of absorbed by the material, or it could be transmitted and go right through, okay? And in reality, very likely all three of these things are happening in some different proportion, okay? And so the green, the yellow, and the blue summed up will always equal the red, okay? One of these three things is happening to all of this incident sound energy: reflected, absorbed, or transmitted, okay? When we're talking about absorption and materials we use to absorb the sound, we're going to be looking at different material properties and expecting different things out of our material to absorb sound. Whereas if we want to worry about how much gets through this material to the other side, we're really talking about a quantity called transmission loss, okay? And transmission loss can be anything from acoustic ducts like a muffler or an intake system or something like that, where we're sending noise through the thing and we want to understand how much is going to get through it. Or it could be a true barrier like a car door or the wall in your apartment. Why do you always hear your neighbor, in all of their conversations? Well, you have poor transmission loss, and so most of the energy that they're generating on their side of the apartment wall is getting right through, and you can hear everything they're saying, right? So absorption, we're worried about kind of trapping the sound. Transmission loss, we're worried about either reflecting it or absorbing it. I just don't want it to come through, right? Okay, so let's look at these one at a time. So sound absorption, it has to do with trapping the sound energy inside the material itself. Okay, so we set this up to test by making sure none of it can be transmitted We have a hard reflective, highly reflective surface at the back. This is our material that we're testing to evaluate for absorption. And so we're going to measure how much sound comes in and how much sound reflects back. And essentially the difference between these two numbers is how much got lost or absorbed inside the material, okay? And you can see some of these alpha, this coefficient is really the ratio of the reflected to the incident. And so we subtract that from 1. So it's always a value between 0 and 1. And so high absorption means almost all of it got trapped in. This will be typically something like a foam, something that absorbs sound very readily. Whereas something like a brick wall is going to be very low absorption and most of the sound is going to be reflected. And so we'll get a very small number for our alpha here. Some sample values show up over here. This is always, as always, a function of frequency because the frequency of sound has a big part on whether it will be absorbed well by a material sample or not. So if we look at some of these effects for a given thickness or a given material, if we vary the thickness, so you see this is a plot versus frequency and how much it absorbs. So higher is better absorption performance in this diagram here. If we have 30 millimeters of thickness, we get this sort of pink reddish trace, and we see it absorbs pretty well above 1,000 hertz, but below 1,000 hertz, the performance falls off. Okay, well, what if we made that same material, but just a thicker sample? We increase it up to 50 millimeters, and you see it increases the performance broadband, but the biggest effect or biggest improvement is at the lower frequency range, right? If we go so far as to triple it to 100 millimeters, you see the high frequency performance does get a little bit better, but not very much. All of our improvement is at the low frequency end. Down here at 100 hertz, you see how much our improvement is in the absorption coefficient, okay? High frequencies, because they have very short wavelengths, are as a result very easy to absorb in a foam or something like that, whereas the low frequencies are going to have long wavelengths and are going to be harder to absorb, okay? And let's take a look why that is, or maybe a strategy for increasing your absorption performance. So if we see these blue dot or the gray dots oscillating back and forth, this is sort of the air molecules in a oscillating tube or a duct here, let's say, and we have a hard reflective wall at the end, and so the air molecules aren't moving at all there, and we see the pressure fluctuation at a single frequency by the orange trace there, right? Well, you see these blue sort of nodal molecules aren't really moving at all, right? And that's because the pressure is phase related to the particle velocity, and that those are offset by about 90 degrees, okay? So the areas where there's zero pressure is where the air molecules are moving the most. Areas of highest and lowest pressure at the wall and at this nodal location here are where the molecules aren't moving at all, okay? And so if we want to more effectively absorb noise for a given frequency, we want to put the material where these molecules are moving the most, because absorption really relies on friction and breaking the sound wave down and into friction and ultimately dissipated as heat. And so that works most effectively where the particle velocity is highest. And so we could put a piece of material that's, you know, this thick against the wall and get performance X, or we'll get essentially the same performance if we use half as much material, but we space it off of the wall and put it at this quarter wavelength away from the wall and maximize the mass of our material to its performance. Okay, we want to put our absorption material where the particle velocity is highest for a given frequency. Okay, so how do we test this? Well, we use this device. It's called an impedance tube, and essentially it's a specialized piece of equipment to test things like absorption, and it includes a broadband noise source. So we're going to generate a high level of broad frequency noise, and then we have this very massive thick-walled tube here, so all the noise energy is trapped inside. Down at this end, we have our noise, or our material sample rather, and so this is what we're testing, is put inside the tube down here. And essentially we have microphones here that we can measure at this positions here. And essentially we're going to generate a certain amount of known noise. It's going to pass by our microphones. We're going to be able to assess the incident sound energy. It's going to go hit that material, and then some smaller portion of that incident energy is going to bounce back, pass by our microphones again, and we're going to be able to quantify how much was going in and how much was coming back, and the difference between those will be our alpha, or our absorption coefficient. Okay. So an impedance tube, it's how we test for material absorption. And so this is a short video. It shows this in practice. You see our two microphones. This is our thick-walled tube. And again, that is to trap all of the acoustic energy inside, so none of it's leaking out or, causing the tube to vibrate and lets any of that energy out. We want to trap it all in there. And essentially we'll make two microphone measurements, and we'll talk later about why that is, but it essentially tells us the direction of the sound flow, whether it's incident or reflected, and then we can do some fancy math and, calculate the difference between those two. So we'll do our microphone measurements, get an FRF, and then we do our calculation, and this is the absorption coefficient for that material. So these are the frequencies it does well at. These are the frequencies that, the wavelengths are a little bit too long. We don't absorb down there. Okay, so that's sound absorption testing. Next up is transmission loss. So again, this is where we're trying to keep sound, or we're interested in quantifying the amount of sound that gets through a barrier or through an acoustic element like a duct or a muffler. Okay, and so here we're going to measure the incident sound power. We're going to measure how much gets reflected, and we're also going to measure how much gets transmitted. And ultimately, this is going to give us our transmission loss number, because we'll have this reflected piece, the incident piece, and the transmitted piece. Whatever we don't quantify as absorbed, but we don't really care what happens to it, whether it's reflected or absorbed. We just want to keep it from being transmitted. Okay. And so again, this will be for things like mufflers or barriers, okay? And a transmission loss plot will again be shown here versus frequency, and here improved performance means you're higher on this plot. So something simple like an expansion can here is shown in very simple muffler design. You see there are frequencies where it does really well at attenuating, and then there are these frequencies where it doesn't really attenuate at all. And these low areas of attenuation are where we're essentially resonating. There's a certain frequency that wants to resonate inside that expansion can, and that's where the transmission loss goes basically to zero, because the expansion can's helping the sound get through. Okay. So how do we test this? Whether it's a material sample or a muffler or a full exhaust system or a whole duct, it doesn't really matter. We put it in the middle of this tube, and you see we have two mics at the front. We put our sample in the middle, and then we have two mics on the back end. And so now we can measure, again, the incident sound energy. We capture the reflected, but then over here we capture how much comes through, and the difference between all of these quantities will be our transmission loss. So same tube that we use for absorption, we just add a second half, two more microphones to our setup, and that's how we measure transmission loss. This is what it looks like in practice. So again, you have these areas of high transmission loss, areas of low transmission loss that, for an acoustic duct like an expansion chamber, you'll have these resonant effects. And of course, this is something that you can simulate rather well. So we have SimCenter 3D acoustic solver. And for more complicated muffler designs, this is the way to go. You don't have to build anything up. You can sort of simulate your perf tubes and multiple chambers and different muffler designs, and get an assessment of how well they're going to block sound from getting through before you weld anything up. I always like to talk about things that you can do in simulation as well. But some of the things we have in terms of countermeasures for transmission loss, one of them is the Helmholtz resonator. And this is essentially the acoustic version of a spring mass damper, if you're familiar with that concept. Same exact principle. You tune it to a really specific frequency, and all it is a volume, a cavity in your duct, and then you attach to your main duct with a certain size neck. And the neck mass essentially is equivalent to the mass in your spring mass damper, and then the volume of air here is equivalent to the spring. And so you tune the neck mass and the volume spring to essentially resonate at a certain frequency, and it'll help you by basically knocking out your transmission loss or drastically improving your transmission loss at a single frequency. So let's look at this in practice. So we have some duct, and we've got high pressure at the outlet of our exhaust or our duct, let's say, and we see this resonance here right at about 350 hertz. So we want to tune a Helmholtz resonator to 350 hertz, and we want to have it help us with this 350 hertz problem. Well, if I put it at the right place, you see the worst location is in blue. That's almost identical to no resonator in red. And so where you put this will have an effect, but again, something you can do in simulation. Optimize the location of this, but if you put it in the right position, you get this green trace, and you see essentially the sound pressure level is knocked all the way down, over 30 dB of improvement at 350 hertz, because it resonates right here and it's out of phase with our incoming sound pressure energy. And so we basically effectively totally cancel the sound pressure at 350 hertz. Much like a spring mass damper, you end up with these two side peaks, but the overall amplitude is still reduced. But this is our operating condition maybe, and that's why we would put in a Helmholtz resonator to help our problem at 350 hertz. Similarly is a quarter wave length tube. So this is our main duct, and all you need for a quarter wavelength tube is a little side branch of a certain length. And this length is a quarter of a wavelength of the frequency you're trying to attenuate. Okay, and it can be any odd number of that quarter wavelength, 1/4, 3/4, 5/4, etc. And what happens is as the sound comes down here, the sound energy branches. Part of it goes up here and part of it goes down your main duct. But what happens is it goes up here, hits the end, and bounces back. But because this is a quarter wavelength, once it's traveled there and back, it's now a half a wavelength out of phase with the incoming sound, and that means it's out of phase, and it will help to cancel the sound energy traveling downstream. So let me show you a simulation where this gets highlighted very well. So you're going to see high amplitude pressure oscillations, red and blue next to each other, red being high, blue being low. And you're going to see these high amplitude pressure fluctuations come down here, kind of go into the split here. They'll come down here and bounce back, but when they rejoin, they're going to be out of phase, and you're going to see red when there's blue right here, and you're going to see blue right here when there's red right here. And essentially they're going to cancel each other out, and the output coming down our main duct is going to be sort of middle green, low amplitude. So watch this happen. So there's low amplitude and high amplitude pulses. All of a sudden we now see red and blue at this intersection at the same time. So those are canceling out, and we get this nice sort of creamy green, low pressure downstream in our duct. I'll play that one more time. So we start out with high amplitude pressure, positive and negative. This quarter wavelength tube sets up this out of phase relationship. So now these high amplitude pressure fluctuations are essentially knocked out. You'll see quarter wavelength tuners all over the place in your automotive inductions and exhaust systems. They're relatively easy to package and are really, really effective for knocking out single frequencies. So that's why they're used all the time. So that is our first hour. I want to thank you for your attention. My contact information is on the slide. Feel free to email me with any questions you have, and I'll see you in a little bit for our second part. Thank you.